The installation described is not code compliant. The National Electrical Code, or NEC, requires that all current-carrying conductors be connected to the electrical system and terminated properly. Installing an unused conductor, even if it is not connected, is a violation of the NEC. The reduction in current after adding the third wire can be attributed to the inductive effect of the lighting circuit. When an inductive load, such as a fluorescent or HID light, is energized, it draws a high current surge initially due to inductance. This surge can cause the breaker to trip if the breaker's interrupting capacity is exceeded. By adding the third wire, even though it is not connected, you effectively created a neutral conductor for the lighting circuit. This neutral conductor provides a path for the inductive current to flow, reducing the current surge on the energized phases and allowing the breaker to hold. When an inductive load is energized, the current flow in the circuit is initially limited by the inductance of the load. As the current increases, the inductive reactance decreases, allowing more current to flow. This initial current surge can be several times higher than the steady-state current. When the third wire is added, it creates a path for the inductive current to flow back to the source. This creates a closed loop, allowing the inductive current to circulate within the loop instead of flowing through the energized phases. As a result, the current surge on the energized phases is reduced and the breaker is able to hold. While the addition of the third wire may have solved the immediate problem of the breaker tripping, it is important to note that this installation is not code compliant. A licensed electrician should be consulted to correct the installation and ensure that it meets all applicable electrical codes. Let's delve deeper into the situation involving the HID lights, the tripping breaker, and the unconventional solution of adding an unconnected third wire. The core issue was that a 20 amp, 120/208 volts, 3-pole breaker was consistently tripping, interrupting power to approximately 12 HID lights in the warehouse. The lights were arranged in 3 rows, each powered by a different pair of phases from the 120/208 volt system. Row 1 utilized phases A and B, row 2 used phases A and C, and row 3 was powered by phases B and C. The initial amp readings on each phase were reportedly around 25 amps, exceeding the breaker's 20 amp rating, which led to the breaker tripping after about 5 minutes of operation. The solution implemented involved running a third wire down each row of lights, utilizing the phase that was not already in use for that row. For instance, row 1, which was initially wired with phases A and B, had a C-phase wire installed alongside the existing conductors. However, this C-phase wire was not connected to any part of the lighting circuit. The same principle was applied to the other rows, introducing an unused phase conductor to each. This intervention, despite the seemingly inactive third wire, reportedly resolved the issue. The breaker stopped tripping, and the amp readings on each phase dropped to approximately 15 amps, well within the breaker's capacity. Now let's analyze the situation to understand why the addition of an unconnected wire appeared to solve the problem and why it is not a code-compliant solution. Firstly, code compliance. The National Electrical Code, or NEC, is the standard for safe electrical installations in the United States. It dictates how electrical systems should be installed to minimize hazards. A fundamental principle of the NEC is that all current-carrying conductors must be properly connected and terminated within the electrical system. Installing a conductor that is not connected to any load or termination point is a clear violation of this principle. Therefore, the described installation is not code compliant. There are several reasons why an unterminated wire is a code violation, including the potential for it to become energized through induction, creating a shock hazard. It can also act as an antenna, picking up stray voltages and causing unwanted interference. Now let's discuss the inductive effect. The apparent resolution of the breaker tripping issue is likely related to the inductive properties of the lighting circuit and the added wire. HID lights, like fluorescent lights, are inductive loads. This means that they exhibit inductance which opposes changes in current flow. When an inductive load is initially energized, it draws a large inrush current, also known as a surge current. This surge is caused by the inductor resisting the initial flow of current. The magnitude and duration of the inrush current depend on the characteristics of the inductor, the applied voltage, and the impedance of the circuit. The breaker in question likely tripped due to this inrush current exceeding its instantaneous trip rating. Breakers have two primary tripping mechanisms: a thermal trip for sustained overloads and a magnetic or instantaneous trip for short circuits or high inrush currents. The fact that the breaker tripped after about 5 minutes suggests that it was likely the thermal trip that was activated due to a sustained overload condition caused by the inrush current. Now let's explore how the unconnected third wire might have influenced the circuit. The key concept here is electromagnetic induction. When alternating current flows through a conductor, it creates a magnetic field around the conductor. Conversely, a changing magnetic field can induce a voltage in a nearby conductor. This is the principle behind transformers and many other electrical devices. When the third wire was run alongside the energized conductors, it was exposed to the magnetic fields generated by those conductors. This would have induced a voltage in the third wire, even though it was not connected to anything. This induced voltage could have had several effects on the circuit. One possibility is that the induced voltage in the third wire created a circulating current within the wire itself. This circulating current would have generated its own magnetic field, which could have partially cancelled out the magnetic field produced by the energized conductors. This reduction in the overall magnetic field could have reduced the inductive reactance of the lighting circuit, thereby reducing the inrush current. Another possibility is that the third wire acted as a sort of shield, reducing the electromagnetic interference, or EMI, generated by the lighting circuit. EMI can sometimes cause erratic behavior in electrical equipment, including breakers. By reducing EMI, the third wire might have stabilized the breaker and prevented it from tripping. However, it's crucial to understand that these are just possible explanations, and the exact mechanism by which the third wire affected the circuit is complex and difficult to determine without detailed measurements and analysis. Furthermore, even if the third wire did alleviate the breaker tripping issue, it is not a reliable or safe solution. As mentioned earlier, an unconnected wire can pose several hazards, including shock hazards and EMI problems. A proper solution to the breaker tripping issue would involve identifying the root cause of the overload and addressing it directly. This might involve several steps. Firstly, verifying the load calculations. It is essential to ensure that the total load of the lights does not exceed the breaker's capacity. This involves measuring the current draw of each light and summing them up to determine the total load on each phase. The measured current should be compared to the breaker's rating and the ampacity of the conductors. Secondly, checking the wiring. The wiring should be inspected for any loose connections, damaged insulation, or other defects. Loose connections can cause increased resistance, leading to overheating and increased current draw. Damaged insulation can create a short circuit, which would cause the breaker to trip. Thirdly, examining the breaker. The breaker itself should be inspected to ensure that it is functioning properly. Breakers can sometimes fail or become weakened over time, causing them to trip prematurely. If the breaker is suspected of being faulty, it should be replaced with a new one of the same type and rating. Fourthly, considering using a time delay breaker. A time delay breaker is designed to tolerate brief overloads, such as the inrush current of HID lights, without tripping. These breakers have a built-in delay that allows them to ride through momentary surges. Replacing the standard breaker with a time delay breaker might solve the tripping issue without requiring any other modifications to the circuit. Fifthly, implementing energy-efficient lighting. Upgrading to more energy-efficient lighting, such as LED fixtures, can significantly reduce the load on the circuit. LED lights typically draw much less current than HID lights, which can eliminate the overload and prevent the breaker from tripping. In summary, the situation described involves a breaker tripping due to an overload caused by HID lights. The addition of an unconnected third wire appeared to resolve the issue, possibly due to inductive effects or EMI reduction. However, this solution is not code compliant and can pose safety hazards. A proper solution would involve identifying the root cause of the overload and addressing it directly, which might include verifying load calculations, checking the wiring, examining the breaker, using a time delay breaker, or implementing energy-efficient lighting. It is always recommended to consult with a licensed electrician to ensure that electrical work is performed safely and in accordance with the NEC.